Morning. Morning, everybody. Morning. Hey, everybody. Y'all hanging in there? Man, I'm just running wild this morning, guys. And we about got everybody here, getting close. All right. Good morning, everybody. All right. I'm fixing. I've got about 2 minutes. I'm going to go start trying to pull up some the notes here. So y'all give me a second. Okay, guys. Here we go. Good morning, everybody, and let's get rolling. This is a lot of slides here. I mean, it's a pretty long chapter. Now, I will tell y'all that just real quick thought. I looked over the test. I actually have it out in the car. I was running so late. When we take a break, I'll run out there and get it. But it was. I noticed that I had 2 or 3 big questions on there, including I think it was like a 10-point or 15-point describe muscle contraction and relaxation, and describe an action potential. That was that electrical event we watched in the video. How that electrical event occurs. And so I'm going to go over that a little bit detailed. I think it does it in chapter 10. It will go over it. And I think that's on the final too. So that's one that like double down, and you really need to get a feel for an action potential. Okay. And then there was a regular 50 multiple choice out of chapters 9 and 10, terms, stuff like that. And then I think I had 15 of those muscle matching of the 25. So I had 15 of the origin, insertion, and action. And so there's 65 scantronable. And so that means Megan's got to flip it over on the back. So y'all remind me tomorrow morning to flip it over on the back on your answer key. Those 15 origin insertion will fit will be quickly graded by the Scantron. So that just makes it quicker, so I can maybe get them graded before Sunday night. Hopefully, we'll see. I don't know what all I got this weekend. And then we had 10 terms. And then we had somebody trying to come in. Usually when I hear that, that's the sound of somebody trying to come in. I'm not seeing it up here. We had 10 terms, and then we had I think there was maybe 10 or 15 parts of the muscles, superficial muscles, right? That we have to label that picture. Okay, or actually what I think I did, I think I made y'all do 20 for a half a point each, so it's like 10 points. Okay, but something along that lines. That's really close. That's more than you'll get anybody else's. That's a better review than you'll get in anybody else's class. Okay, I promise you. Because I actually pulled it out because I had to run it off yesterday, so I'd have it in the car so I could take it with me for tomorrow, because they're waxing. Don't forget, they're waxing the floor this morning. So please don't walk down don't try to ride the elevator this morning. Just go walk up the stairwell for lab today at 11. They should be waxing the first floor today.
I have a question.
Yeah, shoot.
I know we're cutting out a lot of 9 and 10, so I'm kind of worried about what all we need to study for the multiple choice section since we're cutting out so much stuff.
Well, remember what we said, once we get to all you got to know, once we get specific muscle, there are no other pictures. The only picture is superficial run back. And the only origin insertion of those 25 we marked.
Mm-hmm.
Okay, so anything else in there, maybe there could be some commentaries and stuff in there, like about diseases and stuff, and I'm not going to go ask you what a distal tibia tuberosity is. That's a spot on my knee that's swollen up. You know what I mean? That's not on this test. Just what I'm saying. Okay, but obviously any of the markings parts, any of those, the terminology at the first of chapter 9 is gained. So once you get to where he starts talking about facial muscles or whatever the first section is, then all you got knows what we did on those tables.
Okay.
And if there's a random point or two in there or something else, then I mean, that's just life, right? There'll be a bonus. So consider that a bonus. It's just all about how you want to make it, right? Y'all's personal attitude toward it, right? But if I got 105 points, I mean, I could randomly have something in there that I didn't mean to. But I think that's still pretty close. Is that fair enough? Was that Sadie? Who was that? I don't know who.
It was Faith.
Okay, but anyway, but on chapter 10, I'm not eliminating anything in chapter 10 unless I do it as we go. Okay, I didn't preview it, Sadie, so there may be a section I skim through. Okay, but like I said, don't spend 5 hours studying physics of those movements and stuff. I'm not going to go crazy on that. You know what I'm saying? The planes and all that stuff. Levers, I said that may be a question, but I didn't go crazy on the different types of levers. Okay. All right, here we go. So we're going to start off with just a quick review of remember the 3 types of muscle, right? Skeletal, cardiac, and smooth. And there is a little bit at the end that's where they talk about the difference in their contraction. And I did not go crazy on the test on that, but they could be a multiple choice on that. All 3 of these generate a force called muscle tension. And that means that they all shorten. Now, one of the craziest things to me is that muscles do not push out. Okay, because I know I push against a wall, but when I push against a wall, it's actually muscles shortening back here on the biceps that push against the wall. So keep that in mind. And that was one of the things that always threw me off as a young student was that concept of that. Okay, is somebody trying to get in, or is that just? Shouldn't it show up on my screen if they're trying to get in? Okay. Well, they should have been here on time. I'm moving on. Okay, types of muscle functions they can do. They can create movement, help us maintain posture. And this is one that I thought Ammerman really brought out that I wasn't aware of because it had been years since I had taken an advanced class. But stabilizing the joints is a big deal with muscles. So not only do we have to do movement, shorten, but they stabilize the joints in the body. And of course, generate heat. If you ever get stranded in a snowstorm, keep walking, right? You'll have a better chance of living, generating heat. I would say too, one of the more interesting things is your 98.6 degree Fahrenheit temperature is a product of all those muscle contractions and metabolism. So a lot of the heat that we generate is from muscle contractions. Okay, we already said that the skeletal muscles, they're going back and talking a little bit about the histology. We've already done this. Multinucleated, they're parallel. These parallel fibers extend the entire length of the muscle, right? They're voluntary, they're conscious controlled, and they're all attached. They're attached to the only one that's not attached to another bone is remember the hyoid bone is by itself, but all the muscles attached to bones. Now, the thing we're going to see this morning that I think you're going to really like is this is what we saw. This is a drawing of skeletal muscle. Those red stripes, see the red stripes? Those are actually I'm going to show you what they are today. Those are a protein filament called myosin that's visible with a light microscope. And in this space in between where you see the white, these are actually fibers running like this, y'all, called actin, but they're so small you can't see them. So what's going to happen here is that red part is going to grab the little part and it's going to pull it under itself like your fingers come together. One of the great metaphors I've seen is the fingers come together like this. And this is how those sarcomeres shorten. So when you see a contracted muscle, the red lines all get closer because they pull themselves together, okay? And we'll see in a little bit that the functional unit of a muscle fiber, and a muscle fiber is those filaments inside this muscle cell, is called the sarcomere, okay? So the functional contractual unit of a myofibril, which is the contractual protein in the cell of a muscle cell, is called a sarcomere, okay? And that's going to be really important here in just a minute, okay? So I'll come back to this picture because once I saw that, I'm one of these, if I visually can see something, it makes a lot more sense to me. I just do a lot better if it makes sense. And when I got that little trick of what I was seeing with these red stripes, it really changed my attitude about muscle physiology. Here is 3 muscle cells, remember, individual muscle cells, multinucleated, and they have these protein filaments in it that are going to shrink. They're going to pull together and shorten. Okay. Cardiac muscle cells are only in the heart. They're branched. They have the intercalated disc, which was for cellular communication, right? Those gap junctions that allow them to communicate with each other in desmosome zones, form a tight junction. We don't want any of our blood leaking out of our heart, right? So that's a big one. It is involuntary. And AMP2, y'all will go back and learn how they beat on their own, okay? It's really cool. Y'all will enjoy that. And Ms. Nickens is going to go over that. You'll see how the heart is able to beat on its own. So this is really important to get a feel for this day. And I don't know if there's anything more important than action potential. All of next week really depends on you getting this today. Okay, so if you can walk out of here today and you understand action potential, next week's gonna make a whole lot more sense. Okay, I promise you. Here's cardiac muscle, and we saw the branching. We saw involuntary, only found in the heart and hot dogs. Right? There's a joke there, waking y'all up. But anyway, remember that's hot dog. And the smooth muscle has no striations. Okay, it can be long and flat with pointed ends, spindle shaped. Mainly found in the hollow organs, right, to push food through the digestive tract. Also some of the glandular ducts. It is involuntary. It may be linked with gap junctions so you can get a rhythmic contraction. So if you've ever had those stomach rolling stomach or whatever, then you've seen that, right? That is that muscle fire, and it will fire on its own too. Here's smooth muscle. It is involuntary, right? It changes diameter by shortening, and this is our sphincters and all the muscle. This is chitlins. This is the muscle that pushes the food through the digestive tract, right? Very cool. Matter of fact, I tell a really funny one time. So I was in class one day in lab, and I walked by and I heard this girl, and it sounded like she was maybe breaking wind. Her stomach was going like, and I'm like, so I walked away, and it got louder, less sound, and I walked to her. And so finally I walked over to her and just kind of, leaned over the desk. I said, are you okay? Do you need to go to the bathroom? And she said, did you hear that? And I said, I think everybody around you is hearing it. Her stomach, y'all, was grumbling so bad that, literally I heard it, and I'm deaf, y'all. I drove tractors. I can't hear nothing. And she said, can I show it to y'all? And I went like, hey, okay, you're going to show me a body part. You got to show it to everybody so I won't get fired, Megan, right? I don't need y'all showing me stuff. Right? That's how people get fired, right? So she pulled her shirt up very respectfully, y'all, and it looked like that alien in the movie. You ever seen, oh my gosh, Alien, when the alien pops out and kills everybody, or I'm trying to think, Stargate, when they have those symbiotes that lived in it, looked like a snake inside her stomach. As sweet and beautiful as this girl was, there is no way you could marry this girl, because I'm telling you, man, I would have to put a knife in that thing, man. You know what I'm saying? I would wake up in the night thinking the alien's gonna kill me. And I felt so sorry for her, and she told me about all the medicines she'd been on and all the therapy she'd been to try to settle her stomach. She had extreme irritable bowel syndrome. Unbelievable. It really looked like a snake in there moving, y'all. I've never seen anything like it. And you just never know what people's got going on in their life, right? So you need to try to have a little compassion, right, and love one another. But boy, I tell you, you just never know what people's got going on. Okay, there's a nice summary of the three. I'm sure there'll be some multiple choice questions, Sadie, about these, right, or whoever I'm picking on today. I should pick on Heather or somebody today. Okay, but anyway, we will have this going down, right? We'll see some of that. Okay, now individual muscle cells. Now this is where we're going to get into action potential. They have contractibility, right? We know that. They have excitability, and what this means is that the cell membrane can be stimulated to carry an electrical signal, and that can be triggered by a chemical neurotransmitter binding to it. Some contract when they are mechanically stimulated, just like some touches them. Or in the case of the cardiac muscle, a local electrical signal will make them all beat. Now, conductivity indicates that there is an electrical charge across the cell membrane that can be used to our advantage, okay? All right, now, and then they can be stretched, right? Some of them are very long, and some of them are very elastic, so lots of cool stuff. Now, let's take a look at the cell here. And this is, I think, the part that made that video. I saw several of y'all freak out the other day on the video because they kept calling everything sarcode. Okay, so y'all got to bear with me because I got to make this somewhat interesting for me. It's just my style, and don't judge me. Don't judge me too hard. But how many of y'all, and I'm going to go old school. I'm probably going to embarrass myself today. But how many of y'all have seen the old Batman TV show with was it Adam Ward and when they would hit each other and big pow sign would pop up? And it had the Batwoman and all that. That was a classic 1970s TV show that it was real famous and it's now on replayed all the time. But they kind of made fun of Batman, right? It was not as serious as the new ones that they made in the movie. But y'all remember that everything in the Batman movie at the Bat Cave is a bat. It's the bat elevator, it's the bat phone, it's the bat car, it's the bat boat, it's the bat toilet, it's the bat sink. Everything's bat. And it's kind of silly, right? They had the bat phone, everything's bat. Well, when they got down to naming this junk and skeletal muscle, because the contractual unit of the sarcomere, the contractual unit of the muscle cell is called the sarcomere, they went crazy and named everything sarco, okay? And I did not tell y'all that yesterday. And watching that video, some of y'all were going like, what the crap is that? What are they calling the cell membrane? The sarcolemia. See? You with me? We don't have cytoplasm. We got what? Sarcoplasm now. I want to slap somebody, right? We don't got an endoplasmic reticulum. We got a sarcoplasmic reticulum, right? So y'all, I apologize, okay? But they were smoking the crack pipe and they named everything sarco. So regular cells, cell membrane, now it's called a sarcolemia. The cytoplasm is sarcoplasm. Here is those myofibril filaments I was telling you about. They're going to shorten, okay? There's our stripes inside the cell that we can see with a light microscope. The endoplasmic reticulum is well developed in the muscle cells. Look how it goes around all the myofibrils. And as y'all saw yesterday in the video, the purpose of the endoplasmic reticulum in the muscle cell, now called sarcoplasmic reticulum, is to store calcium. Okay? And remember, calcium was the key to that in the video to muscle contracting. Remember? If you remember this. And so I'm going to give a quick metaphor here, and then at the end, we'll come back and watch that video again. But it's really important to get this. Oh my gosh, what's going on here? My computer's acting crazy. Here we go again. Why are you doing that, sweet computer? All right, are you still sharing? Can y'all see the PowerPoint? I can't. All right, I don't know what it did. Hang with me. Okay, I'm gonna have to, okay, just, can y'all, okay, hang on. Gotta love it. I don't know where that went. That's crazy. Come on, computer. Sorry. I really wish they would wax some other time instead of the summer, because I think it works better in my office. Okay, for some reason it's not wanting to work now. What we got going on? That's taking way too long for that to come up. Come on, guys. There we go. Anybody else impatient? All right. Sorry about this. All right. Sorry about that. Man, that's irritating the crap out of me. Come on, computer, load them up. Okay, here we go. So sorry about that. Gotta love it. Loving technology today. Can y'all see it? Okay, good. Okay, sorry. So basically, the sarcoplasmic reticulum to me is like a shop vac that you bought at Home Depot or Lowe's. And I'm talking about that $500 one. I ain't talking about the $50 one at Walmart. But y'all seen some of those are really big on wheels, and they have a button on them where you can either suck, and you can suck the water out of your basement that flooded. You could suck clean carpet with it, or you can flip it to blow, and you can blow the leaves out of the front yard and blow all the crap out of your carport. So think of this sarcoplasmic reticulum as a gigantic one of those shock vacs. And when electricity is shocking it, or the action potential is shocking it, it is going to go into blow mode and blow calcium out to allow muscle to contract. And when the action potential stops, it goes into suck mode and it sucks all the calcium off the troponin, thereby stopping muscle contraction. So I'm kind of explaining that video a little bit. And I really appreciate several of y'all asked me about it after lab yesterday, and y'all went back and watched it. There's also an action potential video that I may show today if we have time, since I made that a short answer question on your test tomorrow. Okay, but the action potential is part of the first of that video that we saw yesterday. Here they are just showing you how they named everything sarco. And I'll show you in just a minute the sarcomere. You haven't seen the sarcomere yet. I haven't been clear about that, but I'll show it to you in just a minute. So these myofibrils are these long fibers in the muscle cells, hundreds to thousands in each myocyte, these myofibrous filaments in here. The diameter is 1 micrometer wide. That's 1/100th thickness of a human hair. They bundle together, and these are the contractual units of the cell, of the muscle cell. Okay, other organelles are very plentiful. We see lots of mitochondria, right? Because we got to have lots of energy to do all this. So once again, you're going to have the myofibrils of these protein filaments that are going to shorten, make the cell shrink or pull in. And then all these accessory organelles are very important, like mitochondria, needed to do the work. Okay, now we're going to look a little bit closer at it. And so here it is again. There's our muscle cell. Now you can see the stripes in here are the thick bands called myosin. You're going to see in just a second. Now this is a very good picture. Look at this. We pulled out an individual muscle it looks like a fascia, right? And they pull one muscle cell out. So this represents one muscle cell, right, in that fascicula or fascia, that fascicula, excuse me. And look, there's that endomysium gristle, connective tissue around it. In that, actually grabbing that extracellular matrix that William was talking about yesterday, and I really appreciate that. Actually talked to another teacher about your question yesterday. Mr. Hopper, that was really good, very good question. Okay, now look, inside, under the cell membrane called sarcolemma, here is those myofibrils. And look, from one Z line to one Z line, right there is one sarcomere. Okay? Now, you may have saw in the video yesterday too that there are these transverse tubules, which are extensions of the cell membrane that go down into the depth of the muscle cell to the sarcoplasmic reticulum that wraps around these myofibrils, because this is where the calcium is going to be stored. And a weird term is a triad is a terminal cystine and the T-tubule, all of this together is called the triad, where the cell membrane extension goes down deep into the muscle cell to the sarcoplasmic reticulum, which is blue, which is really just a modified endoplasmic reticulum, one of our organelles from chapter 3. Okay? She's going over that, talks about that there. And the sarcoplasmic reticulum surrounds these myofibrils, and they store calcium and release it. So that's my shot vac, pumping out calcium or sucking it in. The transverse tubules are extensions of the sarcolemma into the myofibril, as I just said, and it's showing it to you there. The terminal cystine is enlarged here, and you can see that's where two terminal cystines plus a T-tubule form this triad. That's just this junction where that really is happening. Okay. All right. And so inside the myofibril, then these myofilaments, there are contractual proteins, regulatory proteins, that dictate when a fiber will contract. And then there are structural proteins that align and stabilize the muscle cell. Okay. And that's really important. So it's not just about the actin and myosin, which are going to be the two that I mainly talk about. So let's take a look at those. And here they are. The thick red filament that you see as the red stripe is a protein called myosin. The thin filaments are actin with two other proteins called tropomyosin and troponin wrapped on them. And that was in the video that you can see. Other components of this area include elastic filaments called, titans, and other stabilizing myofibrils. There are a lot of genetic diseases where some of these fibers, stabilizing fibers, don't work, and you have diseases like muscular dystrophy, okay, where one of these fibers doesn't work properly. Okay, now look again, we're going to blow it up. This is a good picture. Here is that stripe to stripe, and here is what it really looks like under electron microscope. So here is the myosin head right here, and the myosin, the whole myosin, with those heads on the end that are the fingers that are going to come up and grab the actin that we saw to make it come together in the video yesterday. So I think just watching that video yesterday was probably a good idea to lay some groundwork, right, to see what I'm talking about today. Now that is a blow up. That is a relaxed muscle. And notice the sarcomere is Z-line to Z-line. Okay, wrapped around the thin filament actin is blue. There is a troponin, a small regulatory protein, and the blue, light blue, tropomyosin that is hiding the active binding site on the actin. So those crossheads want to grab that hole there and contract the muscle as we saw in the video. Okay, all right. And here's some of that elastin fibers in here. They're just shock absorbers to stabilize the whole area. Okay. Now, once again, we're blowing it up. Here is that myosin head, and then the long tail making the middle of the sarcomere. Here is the actin with the regulatory tropomyosin covering the active binding site for the heads, and the troponin is where calcium binds. So calcium is going to bind to troponin and shift this so that the binding sites can open up and we can get contraction, as we saw in the video. Tropomyosin is that long rope-like regulatory protein that twists around the actin, covering the active site where the muscle myosin head wants to grab it. Right there, that's important to get that. Troponin is the regulatory protein that calcium binds to that then makes this thing shift out of the way so that the myosin can grab the actin. And so when we look at this, look, I love this picture. Here is an electron microscope at 38,000 power, okay? 38,000 power, and that's what is there. We have seen these little cross bridges. Here's the myosin right here, thick. That's the red part. And right here, we can see the Z line right here, the Z disc, but you can actually see the actin filaments, and they probably go to right here because this is a muscle relaxed. And when it contracts, the whole thing shortens, and you may have 100 of these in a row on one muscle cell that leads to contraction. Okay, I'm going to pause just for a second because I got a feeling somebody's got a question about this. This is a very important picture to kind of grasp. Any thoughts, anybody? Come on, guys. I know somebody's got to have a question here. Y'all know we've gone way too long without, y'all know y'all can ask me a question. Go ahead.
So you may cover this later, but the A band is where the thick and thin filaments line up together, which create the striations in skeletal muscle cells.
Yeah. Really,
so what about?
But I'm sorry. Go ahead. I'm sorry. I didn't mean to cut you, sir. Go ahead. Go ahead.
But smooth muscle cells don't have these striations. So correct. Is their process of contraction different?
Yeah, we'll show it to you at the end. It's coming. It's kind of weird. I'm not gonna, and I promise I won't go crazy on that. Okay. Because I mean, I'm just saying, but it is in here. Yeah, they do a contraction and they kind of wad up. So it's like almost like taking a piece of paper is loose and then wadding it up is a wadded piece of paper. That's what smooth muscle does. It kind of wads up.
Does smooth muscle have the thick filaments?
They have filaments. Yes, they have myosin filaments and stuff, but they're not organized very well. So think of it like how beautiful this is. And this is very, I mean, look, and I don't want to go get all crazy with y'all, but man, is this not crazy God stuff here? Really? I mean, to think how organized this is, right? I just don't think that randomly happened. I don't want to be preaching to y'all, but this looks very organized. Smooth muscle seems a little more primitive, okay? And we'll show it to you. I promise you, we got a picture in a little while, and I'm not going to go crazy on the differences because I just want y'all to get a feel for this, because this is something that will be mega if you ever take physiology at a higher level class. I mean, this is crazy. And so our drugs work at this level, you know, sometimes to help muscles try to work. Yeah, super. This is probably wasn't known to the, I don't know, maybe the 70s, 80s. This was probably discovered in my lifetime as a student. So when I took this, we didn't really know how this worked. Okay, I don't remember. I don't think we did. I don't think it was in the book. I think this came along in grad school for me. So yeah, it's pretty cool. I'll get that. We'll look at that. But yeah, actually the A band, I believe, listen, I believe this is the thing. I think the A band is the whole region where the myosin and actin are overlapping. That is correct. And that H zone is the part where you don't have, where it's just in the middle where you don't have the overlap. And I used to make people draw a sarcomere, a piece of this, 3 line, and label all the lines. And I kind of backed off of that I don't know, but I used to love to make y'all label all this. And it may be a multiple choice question somewhere in there, but I'm not going to make you draw a sarcomere or two. I've taken that out of my test, but I used to be one of my questions. And I would tell you, so you would be prepared to draw that. But it is very pretty when you see that. And that is the stripes we're seeing on skeletal muscle. So I'm not going to scroll back because this thing is so acting crazy at home. But I think you got it. And then she's going to spend several slides talking about the different bands that we have named. Here's a very cool picture that it's not a test code, but look at this. This is a cross section of those different sections. So here you just see what? The little I band, you got the actin in there, and here you got the myosin and the actin, right? So these are just little wedges cut out of that. So I do like the idea of looking at that sarcomere three-dimensionally. Then we talked about the layers. Remember the fascicula surrounded by meroperma. They're just talking about the bundling again. I'm not going to go into that again. She kind of they won't go back over all the layering again. So she kind of repeats herself. This is the video. I'm not going to play it here, but remember that's the video showing some of that big picture in there. Muscular dystrophy, a very terrible genetic disease found on the X chromosome, is a problem where their dystrophin, which is a structural protein in skeletal muscle that anchors the sarcolemma to the surrounding connective tissue, is not properly made. And these children die usually by the age of 30 or 40. Y'all may remember this was a big telethon every year. Remember, I think Jerry Lewis did the muscular dystrophy telethon every Memorial Day weekend. He raised over several $1 billion before he died a couple years ago. But you always notice it's a young boy is the spokesperson, right? And somebody asked me one time, why don't they use a woman? Well, it's on the X chromosome, and very few women get this. So men have one X, and if you get the gene, you got the disease. Girls could be a carrier and not have the disease. So for a girl to get muscular dystrophy, her mother would have to be a carrier, and her daddy would have to have the disease. And that's very rare. And then somebody asked me one time, well, why don't they use like a 25, 30-year-old sometimes as their smoke bottom instead of that little 6-year-old boy that's so cute? They're all dead is why. So these people die before they get very old. Very tragic disease. St. Jude has worked on this. They actually are doing muscle cell transplant, stem cells, trying to regrow the muscles. But that's just a great application, right, to something to show you how important that structural protein is. Look at that. It is absent in their muscles. Symptoms appear between the ages of 2 and 12. By the age of generally wheelchair bound by the age of 12, and dead from respiratory or cardiac failure by the age of 20. Look at this picture right here. Here's normal cross-section skeletal muscle. Look how pretty it is. Here is muscular dystrophy. The muscles, waste away and they don't function properly because they don't have the right structural protein. They have done, like I said, muscle cell transplants, stem cell into this to try to grow beautiful muscle. A terrible disease. I hope none of y'all have ever had to deal with that in your family. Here she is showing the little finger thing I just did to show how the sarcomere contracts, right? And I think that's kind of cool because the myosin is going to grab the actin and pull it in. I love that video that I showed y'all yesterday. It had all of them at once. Remember pulling in? That's just so powerful. And y'all know I'm a great drawer. I just can't draw that. And y'all know I can't draw jack. Okay, y'all know that was a joke. I'm a terrible drawer. Okay, but it really is, to me, quite amazing what you can do with the video. Don't y'all think? I think they're very helpful. Okay. All right. Nothing much here. More of the bands. They love the bands. There's all those bands. I'm not going to go band crazy, but you may see some of that. Just a little bit of that. Okay. But look, there is relaxed, and here's fully contracted. So see the sarcomere shortens, right? Z-line to Z-line is shorter. And you can see that that's how it works. Very cool. Okay, now, everybody take a breath, because here comes a very tough concept. And here's one of those things, and I don't want to keep saying this, but I hope y'all understand it. Teaching sometimes is very tricky, and you have to decide what do you want to talk about. And I use the metaphor, what came first, the chicken or the egg, right? Do we want to talk about the egg or the chicken first? Well, before we start next week's tour of the nervous system, there is a huge concept that we have to understand, and that is called this action potential. We have to understand it, okay? And I'm going to put it on this test, and I'm going to put it again on the final, I believe. So one of the short answer questions, and they're not a lot on the final because I want to be able to grade it quickly and get out of there, right? So it's mainly multiple choice, is this concept of an action potential. Okay, so I'm going to give it my best. I'm not going to open up to chapter 10 where it's really explained better, but I'm just going to give you an overview here, and then we'll cover it again, probably again Monday, and lecture Monday. So y'all bear with me, and I'm going to tell y'all, the first time I saw this, I was very confused. Remember, I am not the smartest person in this Zoom. I've just done this for 30 years. Don't ask me to work on your car. Don't ask me to operate on you. I ain't going to do it. I'll screw them both up. But I'll do my best here. But you probably need to go onto the study area and watch that video until you get a feel for it. And that's the thing I love about this. Forrest Gump could watch that video 10 times and understand this enough to get the 5 points on the test tomorrow, okay? And we have got nobody Forrest Gump level intelligence in this room. Everybody in here is pretty smart, in my opinion. And I've got to grade y'all's papers, and y'all have impressed me. So skeletal muscle fibers have an electrical excitability cell membrane, okay? Now, to understand that, we've got to talk about what's called a membrane potential, okay? So all of the cells in our body, every cell in your body has this membrane potential. And what that means is the membrane potential exists due to an unequal distribution of ions near the plasma membrane, making the inside and outside have a charge difference between them. And in other words, there's going to be an uneven distribution of these charged ions across the cell membrane. This creates a thin layer of negatively charged ions in the cytocell on the inside of the cell, and the outside is slightly positive. This separation of charge creates an electrical gradient, which is a potential source of energy. Okay, let me show you what I'm talking about. So when a barrier separating ions is removed, they follow their gradient and flow electrically charged, right, from high to low. Potential energy is stored energy, like in a battery, that becomes kinetic energy when it turns on a light bulb or fires up your cell phone. Electrical gradients can therefore be referred to as electrical potential. So in other words, in around 1970 or so, I believe, so maybe earlier, they were doing the original research was done on a squid, a little fish called an aquatic organism called the squid, and they have one large nerve down their back for a spinal cord. So they have a long neuron, okay? And here is a motor neuron, right? And here is that axon. Now, what I'm going to tell y'all is this. When we fire a neuron, an electrical event occurs on the cell membrane that sends electrical charge all the way down the axon to the axonal end, or the synapses. Remember the gap between the axon and the next thing it's wanting to communicate with. And as that electricity transfers down, we saw in the video that a chemical is released in this gap. The gap is called the synapses, and the chemical is called a neurotransmitter. Okay? This is so important because your brain is about 100. Well, actually, here's what I read one time. Your brain contains the number of neurons that are found in the rainforest in South America, which is, who knows, 100 million or whatever, trees. The number of connectors or synapses equals the number of leaves on the trees in the South American rainforest. So your brain is literally millions of these neurons all wired together with these little connectors called synapses. And your personality is how those are wired. Your intelligence is how those are wired, how efficient they work. And it all works off of electricity. Now, I'm going to make it real simple. I do not electrically understand how the phone works. I do not understand how cell phones work. Okay, I'm not that smart. But they take your voice and they convert it into what? Electrical signal, and they shoot it through microwaves, and then that transducer converts it back to sound. Like right now, y'all are hearing me that way. I do understand Morse code though, okay? Morse code's a little bit simpler. You have a copper wire from me to Simone, and I shock it, and it makes an electrical thing that it shocks her. And those shocks are put on a little bell, a little piece of metal, so it goes click, 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 and we spell letters out that way. This is Morse code, y'all. You are sending an electrical impulse from your brain down these neurons to tell your bicep to contract. So to me, this is a little bit easier to understand. It is truly electrical transmission down these nerves, down the cell membrane. And you don't have to be a nerd. Go stick a fork in a 110 and see what happens. All your muscles contract and you do this. Now don't do that. I'm joking, right? but I actually done that before. Okay, and that's not a smart move. I didn't do the 4, but I grabbed a 110 one time, and it'll just make all your muscles contract, and you can't let go. So your body is electrically charged. And so they took pretend this is that squid. They took a voltometer that they bought at Walmart, or used to say Radio Shack, but all the Radio Shacks are closed. And your dad or mother may have one. It has a red line and a black line, right? Like jumper cables. You stick one needle inside the cell membrane, the other needle on the outside. That's extracellular fluid, that's cytoplasm, and you get a voltage reading of minus 90 millivolts. And that means that the inside is more negatively charged than the outside due to those ion distributions. Now, guys, I know this is a little bit of physics, but everybody in here has seen a battery, right? Batteries work the same way. They have a positive and negative end, right? And as those electrons are transferred out, that is how the battery runs down and it powers your cell phone, powers everything, your Tesla car. So you have to recharge it. So you have to have this electrical charge across the cell membrane. Okay? It's just one of those things you gotta trust, and it does exist. We've measured it. Okay? So away from the sarcolemma, positive and negative ions are present in equal numbers. That means the cytosol is always neutral, blah, blah, blah. But there is a charge difference because certain ones can leak in and out, and we even have a pump that keeps this up, and we'll see in just a second. So the membrane potential, the cell electrical potential across the membrane is measured in voltage. It is a difference in the charge potential. It is a very low millivolts. And note it, look, I love it. I'm just going to go ahead and apologize. She says 90 here, and then she says 85. I have done a little research. It is different in different cells of the body. But anything from 75 to 90, I've heard, okay? But she said 85. So there is a resting membrane potential when cells are at rest, muscles not contracting. The muscle resting membrane potential is at minus 85 millivolts, with the negative being on the inside and the positive on the outside. Okay? Now, there are protein channels in here that leak ions in and out, and that's a factor. There are others that are ligand gated. Now look, this sounds really scary. Ligand gated means a hormone or neurotransmitter binds to them and then the gate opens. Others are voltage gated. So when they get shocked by electricity, they open. And others are mechanically gated so that when somebody touches you, a touch receptor, then that fires a sodium channel that causes an action potential that you perceive as somebody touching you, or a sound, or a stretch, or even a vibration. Okay? Now, the two main ions are sodium and potassium that are moving back and forth. Remember, the phospholipid membrane is usually impermeable to ions, so these can't easily enter and out. So they got to go through one of these channels. There's a pump called the sodium-potassium pump that we spend a lot of our cellular energy burning ATP. Hydrolysis means using ATP to pump 3 sodiums out and 2 sodiums in. This pump is super important. It is running all the time to maintain a high sodium level on the outside of the cell and a low sodium, high potassium on the inside of the cell. So we create a situation where there is always high sodium on the outside, high potassium on the inside. Both of these are ions that have a +1 charge. So these are both positively charged ions. Okay? Everybody still with me? This is pretty deep. This is some deep physiology. Okay? The sarcolemma, the cell membrane of muscle cells, have millions of these pumps, and they maintain a steep concentration of sodium on the outside and potassium on the inside. This gradient is critical in order to do the action potential. Okay? Thus, essentially, this is essential to the membrane potential and a action potential or muscle contraction. All right. So we're going to talk about that some more. This concentration gradient is the main factor that determines the movement of uncharged molecules like oxygen and glucose in and out of the cell. Oxygen is always going from high to low. But these ions create an electrochemical gradient. Okay? And the overall electrochemical gradient, the sum of these two forces, one drawing potassium into the cytoplasm, right, and other drawing out. So we're going to see some of that's out. And so long story short, there's always some potassium leaking out. Okay, but because of that leakage, that also sets up this negative charge on the inside. So sodium concentration gradient favors movement of sodium ions into the cell. The electrical gradient also favors the movement into the cytosol of that tube. So anyway, long story short, these leaky channels create that resting membrane potential, which is still just only recently discovered how that works. So to get to this resting state, some of these ions are diffusing in and out, and you end up with this high levels of sodium on the outside, which are whatever color that is, purple, and then potassiums are blue. Okay, that creates, and that leaking of sodium out, and of the potassium out, more potassium leaking out than sodium creates that negative charge right there that we see. Okay, so high sodium on the outside, high potassium on the inside. Now watch this event. Now we're going to watch the electrical event. So here's the cell membrane with no charge. This is, she goes back and goes over that again. No charge. But because those potassiums are leaking out, more of them leak out than sodium come in, and that's what sets up that gradient. Now, I don't have time to show you that video, but if you want to watch that on the PowerPoint, you can download it and watch it. But she explains how that inside becomes more negative than the outside, right? If you have more potassium leaking out, then that's going to become negative, and the outside gets positive, and that's where the resting membrane potential is created. Okay, so all of that to say.
I have a question.
Okay.
So since both potassium and sodium are positive, do they affect the charge? Because how do they affect it? Since
I'm going to show you. I ain't done it yet. I promise we're getting there, but thank you. Good question. You're thinking. Okay, that's what threw me out. Whoever that is, I promise you, I had that same thought. Because shouldn't one of them be negative? You know, I mean, that blew my mind, but let me show it to you. It really is cool. So in other words, both of these are positive ions, but we spend a lot of energy to build up this what? High level of sodium on the outside. Let me go back to this one right here. That's what this is normal resting point. Look, all the sodium's on the outside, which is plus charge. All the potassium on the inside is plus charge, but that potassium is leaking out more than sodium leaks in, and that creates the minus 90 millivolt. So what we're going to find out is to get that electrical event to run down the cell, we're going to bring sodium in, and that makes it go positive, and that causes a wave all the way down, and then potassium is going to leave to reset it to minus 90. So you do use two positive ions. Let me show it, and then I'll come back and let you ask that question again. But let me show it to you, I promise. We're going to get to it. So now we're going to do it. Now I'm going to put this in a way that I think this makes a little sense. So imagine this is a neuron in your toe, and you drop 500 pounds on your toe, or your daddy backs over your toe with a car. That is going to stimulate one of those pressure receptors, mechanoreceptors, receptors, and sodium is going to leak in. That's going to send an action potential to your spinal cord that tells your brain you got a darn car on your foot. Okay, so watch. An action potential, this electrical event, is a brief change in membrane potential of the cell from resting to positive, then back to minus 90. Generating by opening and closing sodium and potassium channels, you get this event. The membrane experiences a rapid and dramatic change in movement of sodium and potassium that creates a wave of electricity that travels all the way down the axon. Okay? Now, and here's a word you haven't used before. When to begin an action potential, you have to have two stages. The first is a depolarization that begins when a sodium channel opens and sodium rushes into the sarcolemma. Okay? So if it's minus 90 and the sodium comes in, it's going to go what? Positive. If you reach a positive 30 millivolt, that triggers a chain reaction that opens all the sodiums down the chain. Okay? And I'm going to show it to you in just a second. As soon as that event occurs and all the sodiums open up and you get a wave of positive, right behind it, the potassium channels open and potassium leaves the cytoplasm, goes out into the extracellular and lowers the resting membrane potential back to minus 90. Now watch it right here. It's actually pretty good. Okay, here we go. Somebody stepped on my daddy backs over my toe. Sodium channels pop open. Look what happens. Sodium rushes in, and now the membrane goes from 90 to what? Plus 30. And now that triggers an electrical event that's going to go and cause the next sodium channel to pop all the way down the line. As soon as that happens, potassium channels open. Potassium positive leaves and now it goes back to 90, and now it resets, it's ready to fire again. Is that not the craziest thing you've ever seen? Now, how do we get the ions back to where they need to be? The sodium potassium pump is always pumping sodium out and potassium back in. So that resets the ions. Do you get that? Do y'all see that? I can attempt to draw it here. I got a little piece right here. Let me see if I can draw it right here. And y'all know me in drawing with this little pen is not going to be pretty. Let's see what I can do. Let me get a small. So in other words.
Hey, Mr. Robison,
Go ahead.
Jasmine had to rejoin because our power went out. She says she's in the waiting room.
I don't know how to get to the waiting room here. They need to figure that out. There it is. I don't know how to get them in. They're going to have to get their butt here on time.
No, she was in the lecture, but our power went out.
I know. I'm being mean this morning. I'm sorry. But, dang it. Hang on. Act of Congress here. We got 3 people waiting out there. I'm sorry, guys. I'm sorry. Sorry, guys. Yep, y'all, they got to tell me because I can't see that room. Can't see that. Sorry. We got everybody in now that's in the waiting room? Sorry. Okay, so let me draw it real quick, okay? And I'm going to try and please bear with me on this picture. So we have high levels of what? I've got to go back to pen. Sorry. High levels of sodium on the outside. That's me trying to spell sodium, a positive ion. And the levels are what? Very high. That's the up arrow. Potassium is very high. Once we get stimulation, these sodium channels open and they rush into the cell, and that's going to make the inside that was already what? Negative, right? Remember, it was negative. Now you bring a positive in, and that's going to what? Make it go positive, right? Everybody see my pluses? I'm trying with my pen and my mouse. So this wave of electrical change is the action potential. So sodium channels blow open all the way up and down, and that change triggers that to happen. So sodium rushes in. These are sodium channels I'm drawing. Now, that wave of electricity is the action potential. That's the same as me taking that electrical wire. If Simone had a copper wire right now in her house and I had a copper wire, I could just shoot a little electric charge down it and it would shock her. And that would make her maybe wake up or whatever, right? When she is awake, I'm looking at her. But that is how this works. We send electrical impulses down living copper wires called axons. So this is a living cell membrane that we're dealing with that serves as copper in like a Morse code or a cell phone. Not the cell phone, but old copper phone wires. The little phone is turned by sound into electrical pulses that your phone on the other end of the copper turned it back into voice. Thank you, Alexander Bell. Now, as soon as this happened, look, and I can't change the color. I wish I was smart enough to change the color here. Oh my gosh, I'm finna go crazy on y'all. Look at this. So as soon as this happened, what else is gonna open up? Watch this. This is gonna look really good. We had high levels of what on the inside? Potassium is red. As soon as that sodium channel pops open, now the potassium channels are gonna blow open. These are potassium channels, red. Watch. And now potassium opens up and it rushes out. Everybody seeing this? And what happens now to the charge? It goes back negative. Matter of fact, it goes back minus 90 millivolts. That's what we're seeing right here. Oh, now I got it on top of everything. Oh, that's great. I love it. I just colored on top of everything. Okay, but look, that's what we're seeing right here. Look, sodium opens here. This is a voltometer. This is your voltometer. It goes plus 30. Then the potassium channels open and carry it back down. And so action potentials are like a gun, a bullet, a pistol. They fire or they don't fire. You pull the trigger, you get a bullet. Action potentials are all or none. They either fire or they don't fire. And so check this out. How if we blindfolded one of y'all and we had your boyfriend or husband kiss you on the cheek, then we had your worst enemy slap you on the cheek. How does the cheek know the difference between a kiss and a slap? It's the number of action potentials the brain gets. Somebody kissing you is this. Listen to the sound. I like that. Somebody slapping you is. So it's all about the number of action potentials per second is how we determine intensity of stimulus. Wow. Is that not cool? Really, it's a fundamental thing to understand. So your brain works this way by sending these action potentials, these electrical events in your brain. All right, thoughts?
I have a question.
Yeah, please.
So basically, action potential is just creates that chain reaction for muscle contraction and relaxation.
Yes, yes. So contraction is, all this is setting up to show you how muscles contract. Exactly, William. And that's William, right? So I can't make sure who's talking. But yes.
It's Albert.
Okay, Albert, I'm sorry. So really what we're doing here, this is the setup to tell us how the muscle to contract. That's right. So it's kind of like the chicken or the egg. We had to explain action potential before we could explain muscle contraction. But action potential is actually in chapter 11. So we get a little review of this again on Monday. Yeah. Yes, all this is just to set up the video I showed y'all yesterday. Yes. And the very first, remember showing the electricity coming down to the synapses? That is this electrical event. And when the electricity reaches the end of an axon, it triggers the release of a neurotransmitter, usually across the synapses, which is the gap, that then tells the brain something else, or in the case of chapter 10, it tells the muscle to contract. And when we stop the action potential, we stop the stimulation of the muscle, you stop picking up the chair. All right, thoughts? I'm going to erase this because I can't go forward. Does that help a little bit me drawing it?
Yes.
I actually thought that's pretty good for me with as difficult as this is.
Just to clarify, so action potential happens in the axons of neurons.
Hang on, I think, you know what? I didn't record this freaking thing. Are we recording? I think I turned it on, didn't I? Yeah, it's recording. Say it again.
So actual action potential happens in the axons of the neurons.
Yes. And the cell membrane of the muscle cell and the cell membrane of all your cells in your body when you stick your fork in a 110. I was just trying to add a little to it. So yes, in the contents of our test question tomorrow, it is the action potential on an axon or neuron coming down to the muscle cell membrane that triggers the action potential. That then transfers it to the cell membrane of the muscle that goes down to the sarcolemma and causes muscle contraction. That goes down to the endoplasmic reticulum, sarcoplasmic reticulum. We're going to go back and watch that video again real quick. I mean, at the end, so that you see it again now that you've learned it. You know what I mean? That I've explained it a little bit better. The video makes a lot more sense. And if we don't have time, I would just go back to that study area and watch it again on your own tonight. I think I'm going to have time to do it again today, because this is really the main concept. You know, there's two big things: action potential we've got to look at, and that muscle contraction. But we've done it once. Good question. Anybody else got a question? Guys, I really do appreciate the questions because it makes me rethink what I'm saying. Anybody else? There are no bad questions, just bad teachers.
I have a question.
Oh, shoot.
Well, it's more to clarify. So pretty much when your muscles aren't stimulated, you're just kind of sitting here and your cells are filled with potassium. You're okay. And it's negative because you're not, moving.
Because that's the way God made it. Yes, negative because that's just the way God made it, because the leaky channels let more potassium leaks out than sodium leaks in.
And then all of a sudden someone pops you in the face. And so then they're like, your muscles are like, oh, someone just hit us. So we're going to put sodium in the cell and put potassium outside of it. And then That's how you get the charge.
Yeah, that's how we get the electrical event that tells your brain that somebody slapped you. Yeah.
Okay.
Yeah, you got real good. That's really pretty close to the deal. So in other words, this event we just covered happens anytime any receptor in your body is stimulated. Matter of fact, listen to this. Photoreceptors in your eye detect wavelengths of light that trigger an action potential to the brain that you recognize as a color. So vision even uses action potentials. Your ears are detecting different frequencies of sound that then trigger specific action potentials that your brain determines as a note. Is that not crazy? So you can close your eyes and you can hear your mother and recognize your mother's voice versus your daddy's voice, because we fire different action potentials to our brain. So man, this is so cool. Yeah, go ahead.
Oh, I'm sorry. So what triggers action potential, or is action potential the trigger?
She was real. Okay, if you'll back up, and I'm scared to even back up, but remember it talked about the different type of receptors, which we really don't get in. Okay, the maestro corpuscle in lab, light touch. I lightly touch your arm, that squeezes that maestro corpuscle, and that causes sodium to pop in, and that's what starts it. So for mechanoreceptors, it's touch.
Okay.
For pain, there are the receptors in your skin that detect pain that's been released, pain neurotransmitters. So, but to me, the touch receptors, they just one. Maestro corpuscle, we've been talking about for 2 weeks. And Pacinian, remember, it was deeper in the skin. So receptors seem to work good. And that's why I dropped the weight on the foot. The foot metaphor works for me here for your first look at this. I did, so dropping, I would, back in the car over my foot. Does that make sense?
Mm-hmm. It does. Thank you.
Thank you. Now, look, those are the good questions. And now, look, you were brave enough to ask a question, but I think you helped 15 other people understand the concept. So, y'all, I was telling my boss last night that I really like the Zoom because y'all ask more questions on Zoom than y'all would sitting in a classroom, because you're used to talking to your buddies and stuff on the phone, video chatting. So I do like this. I just wish I had another monitor where I could be watching all y'all. So I'm just kind of scrolling through. I'm not moving around watching each of y'all a little bit. Okay, anybody else on that? Very good, good stuff. So check this out. She makes a point here, and we'll see this later on in chapter 10 video, okay? Look, action potentials don't stay in one place. They are conducted or propagated throughout the entire cell membrane of the muscle, like a ripple on the surface of a pond when you drop a rock in a pond. The process is very fast, resulting in depolarization of the entire sarcolemma cell membrane, including those T tubules in the muscle. Now, we'll come back on Monday and talk about action potential some more, but I think y'all got a really good idea. That's a 5-point question on your test tomorrow. Describe an action potential. Okay? Now we're back looking at the action potential in the muscle cell. So as we get an electrical event on the cell membrane of the muscle, the sarcolemma, it travels all the way across it and goes down those T tubules. Okay, now watch. Here we go. We're going to go back up. So here's the neuromuscular junction now that we kind of know a little bit about it. I'm going to get the picture. Please hurry up, picture. Okay, here we are. Here's the axon coming down. Here's electricity coming down. It reaches the end, but instead of arcing across like a spark plug or lightning, there's no lightning in the body. The neurotransmitters are released by exocytosis into the gap called the synapses. They're going to go across, and that's a nice video there. I'm not going to play it, but y'all can go back and look at that. Those are also in the study area. And here's a great video, because I don't have the PowerPoint running, but it shows the neuromuscular junction. I'm going to get down to show it to you if she'll let me get on down here. Okay, man, going on too long here. Hang on, let me find the picture. I like pictures. Here it is. So the neurotransmitter goes across, binds to receptors. This is the cell membrane of the muscle, the sarcolemma, and look what comes in. Sodium rushes in. You reach that threshold of plus 30. You get an electrical event now that's going to go all the way across the cell membrane. Everybody with me? In other words, now the electrical event's going to what? Go both ways, right? Bam. So now we transmitted an electrical stimulus from what? The axon through the chemical neurotransmitter binding here. Sodium rushes in, and we go positive in here, and we get the electrical event. So the action potential is once that threshold is started, all the sodium channels pop open all the way down the cell membrane. One of the coolest things I think God made here. Really cool. Okay. Sorry, I got to erase it, or it stays with us the whole time. Okay, I'm learning how to play with this a little bit better, so I apologize. I'm getting there. Okay. Now, this is the video I showed y'all last time. Okay. That I'm not going to play it right now. I've got to go find it another place because I'm running this off of PDF. But this is showing you that. So look, remember it started and it's in there and it has even questions y'all can take. And here they are in here. It's just going to be, I don't have the video to play, so I'm going to skip on through that. We may go back and show it. Let's finish the chapter. And we'll end by going back to that video again, because that's the 15 point or 10 or 15, and I'll go look at my test to make sure it's 10 or 15 points. So I'm going to skip through this, and we will come back and watch that video, but I've got to go into the study area because I'm not actually using PowerPoint here. Okay? And so here it is. Here it is. So look, sodium comes in, action potential travels down these sarcolemma, down the T tubules to the endoplasmic reticulum, blow it up, video for all that, and it's in the PowerPoint. This is all part of the big picture that I showed y'all yesterday. But she has the pictures. We can do it without the video because I have the pictures here. Give me a second. This thing is moving slow. We're going to take a break in just a second. So hang on. Break's coming. A lot of wasted slides here. Come on. Here we go. Here he is. Now look, here's the calcium coming in, binding to the sarcoplasmic reticulum, and that's going to open what? Calcium's now going to rush out, and it's going to go bind to troponin. And look what happens. When calcium binds to troponin, the tryptomyosin, the blue band, moves, and now the active sites are open. And we can now get our cross bridges to occur. I hate I got all these pictures in here, these questions. But they will answer the questions for you if you do it online. I'm getting to the picture. Bear with me. She uses not enough. Okay, so look. So now that we've got calcium binding, we get the power stroke, and the muscles then do the finger thing, right? By the myosin grabbing the actin, we get the row your boat called the power stroke. There's the video I showed you yesterday. It's going to pull it in. And we're going to get a contraction of the muscle. If I can get the pictures up. Sorry, this is getting on my nerves. Lord, I wish those guys had waxed sometime in the regular school year. I do think I like my PowerPoint. We got a picture somewhere here. There it is. So here it is, relaxed and now shortened. So the sarcomere shortens. Another video you have in the study area. Okay, they use the sailors pulling the rope to pull it in. That's a metaphor. Relaxation occurs when the neurotransmitter stops releasing acetylcholine. There is an enzyme in the synapses called acetylcholinesterase, and it destroys acetylcholine. So then we get a stop of the action potential. We stop the depolarization of the sarcolemma. And then when the sarcoplasmic reticulum is no longer being activated by the electrical event, calcium then is pumped back into the sarcolemma, back into the sarcoplasmic reticulum. It pulls, there it is, there's acetylcholinesterase that destroys it in the gap. The calcium gets pumped back in. Look at this. Now the electrical event stops. Calcium is pulled off troponin. Now it slides back in and covers up the cross bridges so we can't contract, and now we've relaxed. So relaxation is caused by stopping the action potential at the neurotransmitters being destroyed in the synapses. And then that leads to the sarcoplasmic reticulum switching to suck calcium instead of blowing it out. As I said earlier, the sarcoplasmic reticulum, when it's being electrocuted, it releases calcium. When it's not being stimulated electrically, it goes into suck calcium up. And here it is. Here's that mechanism. So now that it stops, right, then it's going to pull it off. It's a review. That's a big picture review. All right. Now, I would love to go over that video again, but we did watch that yesterday. Is everybody okay with that? Comments? Thoughts? I need, if we have time, we need to finish the chapter. We'll go back and watch it again. I'll pull up the study area. But I think if you would watch that video again, I know, how many of y'all watched it last night? Anybody go watch it? Oh, did y'all take a night off last night? Oh, a lot of people took a night off. Okay. We don't have a test today, but I really encourage you to watch that again tonight if we don't have time today. Okay. Now, what we're going to do now, we're 149 of the 213 slides. Let's take a 5-minute break, and then I'm going to come back and just finish the chapter. Then we'll go back to the video and watch that video again now that we went over it. And I think that y'all feel a lot better. But if we don't have time, I'll leave that up to you to watch it again. Okay. So 5-minute break. I'm going to run and get my book out of the car, so I can take roll and all that good stuff. Okay. And I can tell you more about the test. And y'all can think about a question if y'all have. And y'all know I don't mind. I really, really do appreciate y'all asking really good questions today. Okay. All right. Take a break. Take a break. I'm going to run get my book. Okay, we got everybody back. Y'all about ready to get back at it? See if I can get this thing to get back where I want it to be. Darn it. Okay, guys. Okay, let's get started back as I'm trying to get it all covered. Sorry, I know some of y'all are getting kicked out, and y'all just have to. I'm not. It's not popping up on mine when y'all get thrown out. So please, just if somebody sees somebody in the waiting room, just tell me, and I have to hit a little button here. Please let me know. All right. I think I've got 28, 7 of y'all here. I think it's maybe Michaela McCarthy. Is she here? I think Michaela's not here. She may have withdrawn. I'm not sure. Michaela, she was here yesterday. So I'm going to count her absent until otherwise she speaks up. I got everybody else is getting in and out, trying to get in. Okay, while I'm thinking about it, before we finish the chapter real quick, I've got 50. I'm looking at the test, 50 multiple choice, like standard. I've got 15 of the origin, insertion, and actions. That's 65 points. I got a 5-point question on action potential. I got a 10-point question on skeletal muscle contraction and relaxation. Then I got another short answer coming from the next few minutes lecture. And I think y'all figure out what I get excited about. So there's another short answer on this last hour of lecture, or excuse me, 40 minutes or 45 minutes. Then I got 10 terms. So let's see what that comes out to be. 65 multiple choice, 75, 80, 83 points, 10 terms, 93 points. And then I've got 12 labeling the muscle for a half a point each for 12 points, making it a 105-point test.
Were
So,
the sorry.
ma'am,
Hello? Okay. Were the terms, was that from the chart in chapter 9?
I didn't say it's just no, it's just like it could be any major term anywhere in the book, anywhere in 9, other than, it's not a label or anything, but it's not necessarily from the tables. It's words, out of the chapter.
Okay, never mind. I see. Okay, yeah. Okay,
You got me right. Most of what I've already said, and I think I'm looking at it right now. I've got several of them coming up. Actually, I'm going to say most of them may very well come from what we're going to cover. I'm just looking at the terms here. I think a lot of them are actually going to be in the last 30 minutes of this lecture. Okay, actually, I'm looking at it. Yeah. So nothing major here, but several of them are going to come out of this. Okay, I believe coming forward. If it don't, I'll double check because I see one. For example, I'll give you one of them. I see here, Botox. How many of y'all know how Botox works? I think we mentioned that the other day, didn't we? But Botox prevents the acetylcholine from being released, or being, so you end up with you paralyze the receptor from getting the neurotransmitter. You paralyze that muscle. And I'm thinking like, oh, so when ladies get the Botox in their forehead, they can't move their forehead again, so therefore they don't get wrinkles. My mother was having trouble controlling urination, micturition, and they actually Botoxed her entire bladder muscles, called the detritus muscle. They injected her bladder 3 or 4 times with a long needle. And so a lot of people who have problems with controlling that, it's not the sphincter, it's just irritable. The muscles are contracting randomly in her bladder, and this paralyzed them so they would not randomly contract. And it's very helpful to her. It's really changed. It's been a big quality of life thing for her that you wouldn't think of it, something like that actually helping, but it did help her a lot. Okay. Okay. So next little part here, just some random stuff here, but there's some of my favorite terms coming up and multiple choice. So where do we get energy for this? Well, one of the problems with this book, the only flaw I really see in this book is we should have had a chapter on energy back in chapter 4 after chemistry, or actually after chapter 2, or maybe between 2 and 3 or 3 and 4. Obviously, we need lots of ATP, and we get this ATP by doing cellular respiration, right? We need power to pump the sodium potassiums out. We need energy for the actin myosin filament. Everything, nothing is free in the cell. You got to burn energy. and we got to have energy to pump the calcium back into the sarcolemmal reticulum for relaxation. So we mainly get our energy by oxidation, but we take sugar, we break it down by glycolysis in the cytoplasm, and by aerobic cellular respiration or oxidative catabolism in the mitochondria. For every sugar molecule that we run through glycolysis and the aerobic oxidative, that's aerobic respiration, we make 36 to 38 ATPs. That's what most books say. And that represents about 45% of the energy in the sugar molecule. So we convert the bonds, the power in the bonds in sugar into ATPs at a ratio of about 45%. Now, somebody in this Zoom right now is going, well, Robin, that's real inefficient. Actually, that is exceptionally efficient. Nobody is driving a car, and I've looked in the parking lot, and most of y'all driving a vehicle better than mine, and which is great for y'all, I guess, but a poor teacher, not for me. But I would say a Prius is the only thing getting 45% efficiency rate in the gas. So unless you're driving a hybrid or a Tesla, you're very inefficient. Those big Yukons and those big trucks, they get 20% efficiency. A Winnebago or a semi-trailer truck probably gets 5% efficiency. So and your air conditioner is probably, if you got an old air conditioner, I got a 20-year-old here at the house, it's probably running at a very low efficiency rate, maybe 25, 26%. I had a friend of mine build a house, y'all, built $1 million house and put the best insulation and stuff in it. I think it's like 4,000 square foot house. And I got like maybe 20, maybe, I don't know, maybe 3,000 here. He's got like a 6,000 square foot house. His power bill is 50% of mine because he put high efficiency heating and cooling system in that you just don't get unless you pay big money for it. So something to be said about efficiency. And that's a whole nother story. I won't go off on that as I just did, sorry. But we need energy, and this is how we do it. We do cellular respiration, which is going to be covered in the digestive chapter. Okay, now here's a term. Sometimes we need extra energy that we can't make it quick enough. So we store energy in the muscle in a compound called creatine phosphate. And it can convert the burnt ATP, which is called ADP, back to ATP 5 to 6 times faster than cellular respiration, burning sugar and doing this. Now, this is really interesting because a lot of weightlifters and athletes take creatine as a supplement that is actually tinkled out in your urine. So theoretically, taking creatine supplements may help you with endurance. That has not been scientifically proven, but since we tinkle it out, we are using it up. Maybe buying that, taking that in our diet helps us get more endurance in our training and endurance training. That has not been banned by any sports agency either. So here it is again. We have stored ATP. We use it up. Then we can convert creatine phosphate, can reboot the ADP back to ATP very quickly. And so creatine phosphate is a stored energy, kind of like most of y'all have a four-wheeler that has a little reserve tank on it that holds like a half a gallon to get you somewhere after that, right? And so that is a reserved energy tank in muscle cells. Glycolysis is the first one that does not need energy, right? So we can convert sugar into pyruvate and we end up making ATP a little bit. It's not very efficient. This is anaerobic respiration. But all of that glucose is used up within 30 to 40 seconds of a sustained contraction. So then we have to go and we have to have oxygen to do aerobic cellular respiration. Oxidative catabolism requires oxygen. If you don't have enough oxygen, if you can't breathe enough in, then you convert the pyruvate to lactic acid, which is later converted back into sugar. Now, one of the things that we've been teaching that's wrong is we now know that this lactic acid buildup, we thought for a long time that caused the cramps in muscles. It has now been proven that that does not cause cramps in muscles. And we'll talk about that in a minute. That's coming up in a second. But we do have a lactic acid buildup, but it is converted back into sugar and carried through aerobic respiration. Now, I'm making no sense to y'all because y'all probably don't know that because we haven't covered it yet, but yet we're still going to make you know a little bit about it here. Still think that energy would have been better in earlier this semester. Here it is again, showing it to you again. We can this is a summary of the energy that we didn't cover. Glucose from the food can be converted into 2 ATPs by glycolysis. If we can't do aerobic respiration over here, then we can make lactic acid. But normally, and if you're in shape, after you make 2 ATPs, the pyruvic acid is then converted through the mitochondria into carbon dioxide, and you make 34 ATPs over here. So lots of ATP made here. Aerobic oxidative catabolism or cellular respiration is the key. But we have to have oxygen, and here's another term, one of my favorite terms. Why is meat red? Because the myoglobin is a compound like hemoglobin found in meat that it stores oxygen. So freshly cut hamburger meat or steak that's red has lots of oxygen in it. If it loses that oxygen, the meat turns brown. So myoglobin is a oxygen storage compound in the muscle so that the mitochondria can have plenty of oxygen to make all this ATP. That's pretty cool. Oxidative catabolism or aerobic catabolism requires oxygen, right? And we can burn sugar or fat into that. Okay. And after a minute, it provides 100% of the energy used. And so myoglobin is very similar to hemoglobin. It stores oxygen in the meat. Which brings me to an interesting question. How many of y'all have ever been to Kroger's or Walmart and seen the meat that they discount on Tuesday or Thursday morning? Like them $20 steaks are now $10, right? My mother would never buy that because it's brown. Well, guess what you get at Como Steakhouse, or you go up to one of the fancy steakhouses, the Ruth Chris or somewhere real fancy. Guess what they guarantee their beef to be? Aged beef, which means they let it rot in the refrigerator. And rotting breaks down the actin-myosin filaments and makes it tender. So one of the funniest things is if you go to Walmart and get that meat been sitting there already turning brown, that's expensive meat at a fancy steakhouse. And when you cook that, you can tear it with a fork. So Robin buys a lot of old steaks. I look through the old meat bin at Walmart, and that's where I buy my steaks because they're already aged. I've ate at a place in New York City that when you walk in to be seated, you see a glass window showing the cooler, and all the meat's laying in there at room temperature, at a temperature of a refrigerator, rotting, and that makes the meat tender. It's called aged beef. It's pretty funny to me. Now, I don't do aged hamburger meat. Hamburger meat's a lot of crap. I would just cook it up and don't eat raw hamburger meat, okay? But myoglobin is really cool. Here's a little comment on creatine phosphate. I just mentioned it as a supplement. Creatine or carotenoid, I've heard it pronounced both ways. I don't know which is right. Big debate on pronouncing that word, but don't overdo it on it. It's probably not good to overdo it. Okay, now different tensions at the muscle level. Let's look at this. So a twitch then is that contraction of the muscle. And we can see it on a physiograph, a electrical, like a voltometer or a myogram. And we saw this already. So don't make a big deal out of this. Let's get the picture. Here's a myogram. We had stimulation, then we had contraction, and then we have relaxation of the muscle, right? Here, the calcium is being pumped back in the sarcoplasmic reticulum, and the muscle relaxed. So one muscle twitch takes about 40 milliseconds. Pretty fascinating.
Mr. Robison?
Yes?
I'm really sorry. Talbert's audio is cutting out, so he had to leave, and he's going to have to rejoin here in a minute. I'm sorry.
Okay, that's okay. Just let me know. No, that's what I'm here for. Thank you. That's cool. I think I figured out how to do it here. I got to hit this button. Sorry. Maybe I can leave this up and I'll see it. See them when they come back in. Yeah, I'm just trying. I don't know if y'all see that. Y'all see that? Does that bother y'all? I'll try to get it out of the PowerPoint way. Still learning out all this stuff. No problem. You're fine, dear. Thank you. So tensions are produced, right? And the tension produced during a twitch varies from several factors: timing, frequency, type of muscle, and the length of the fiber at rest. So basically, that's just trying to walk. And I'm not going to do a bunch of these waves. I'm going to have a bunch of this on the test. We're going to kind of run through this quickly. This is not high probability stuff. Tetna is when you do a sustained contraction, like you pick up a chair. So tetanus just means a controlled muscle contraction. The disease, tetna, y'all have heard of this one, right? Is a toxin that we get in a chemical produced by a bacterium that causes the acetylcholine to be released and never taken back up. So botulism toxin will make your muscles toxins, tetna, is a condition where it just contracts and don't relax. So here is a sustained contraction, like when you pick up a chair or I hold the door open for somebody. Okay. Now here's a little something I don't have on the test, but check this out. There is an optimum length tension relationship. Look at this. Which one of these would pick up the most weight? That is not a good, nobody weight lifts like this. That's not, you can't pick up a lot like that. But right here, there he comes in. I think I heard somebody try to come in. Is that what that was? Okay, I'm not seeing him here. There you go. There he is. Thank you. Got it. I'll try to leave that up going forward. Sorry about that. But here is the optimum length tension ratio. That's when you're going to get the most strength when you have your hand like that. Okay. Then going either like that is real powerful. Like this, you don't got a lot of room because your sarcomeres are almost stretched out. And here, they're almost maximally contracted. But here, it's in a good spot. Here we go. Clostridium botulism, one of the most lethal toxins in the world. As little as 1 gram could kill 1 million people. The toxin is diluted and it blocks the release of acetylcholine at the synapses. And so by paralyzing people's face, they don't get wrinkles. But if it gets on the diaphragm, you will die of respiratory failure. It would paralyze the breathing muscles. Botox is super diluted Clostridium botulism. Totally crazy. Okay. Now, here is our other short answer question. So wake everybody up. This one is on the different types of muscles. Now, I'm going to acknowledge that they have found some other ones, but there's 2 main types of muscle cells. Okay. And I find this super fascinating. This is some deep physiology. There is a type 1 and a type 2. Type 1 is slow to contract. Type 2 is fast to contract. And this classification is also based on the speed at which they can do myosin ATPase and how much energy, their energy source. Okay. I'm going to go down here and show them to you a little bit better. Type 1. Okay. Now let me make sure, because I get these confused myself. Got to be careful. Type 1 is the slow twitch. It is small diameter. It contracts slowly. It produces less force for longer periods of time. Okay. And because it is slow to beat, it doesn't have to have a lot of oxygen. It doesn't have a lot of mitochondria, and it doesn't have much, excuse me, let me get that started again. It relies on oxidative catabolism, a large number of mitochondria and myoglobin molecules, has lots of myoglobin, lots of mitochondria, and a well-developed blood supply. Okay? But because of that well-developed of the blood supply and the myoglobin, this is dark meat. So what muscle on a chicken do you think it uses a lot? I would say, now come on, okay, what's a dark meat chicken? What muscle is dark meat? Come on, y'all know this.
The thigh.
The thigh and the leg. Thank you, yes. So the thigh and the leg is dark meat because they stand it up all the time, okay? So they have more type 1 fibers than they have type 2. Type 2 fibers, look at this, are large showing muscles, fast twitch, they fire real fast, but they fatigue very quickly. They have very little myoglobin, so they don't have that red in them. They have few mitochondria, and this is white meat. Now, we all know what's the white meat on a chicken?
Breast.
The wings, yeah, the wings and the breast, right, for flying. When's the last time you seen a chicken fly? How far did it fly? About 10 feet. So white meat is for quick motions, quick, fast to fire, and it's real big and showy. So let's talk about athletes. Who is the fastest man on earth? Remember Mr. Boat from Jamaica, right? Baby got big butt, right? I mean, that's a good looking man, right? He got big old butt muscles, big old legs, bigger than my fat stomach, because that man his muscles are 100% type 2. He genetically was born with lots of type 2. And in Jamaica, they actually take everybody out in kindergarten and they make them get on the 0-yard line and they run a 100-yard dash in kindergarten, everybody. And the fastest kid gets an award. So part of their culture is to really try to get people to run to be fast. Jamaica is such a small place, right, to have so many world-class runners. Probably got to do with some good genetics, but also training. Now, how many of y'all have done weightlifting? One of the coolest things here is Mr. Weimer, who started Fitness America magazine. I think he's still alive. He's like 112. He's like 100 years old. He may have died in the last few years. He also did the magazine Fitness magazine. He also started GMC supplement company. And back in the 50s, he wrote some articles which are the foundation of weightlifting. It's called the Pyramid Weightlifting Scheme. Y'all may have seen this. And the whole field of kinesiology has spent the last 60 years proving him almost exactly right. So if you can go to the gym and you can convert your muscles to type 2 fiber, and you'll be big, fat, and showy muscles. Get them big muscles. And the way you do that is you do high reps and you do the pyramid. If your max can do 200 weight lift, then you do like 10 at 190, 10 at 195, and then you burn out at like 205, and that tears the active myosin filaments in your muscle, and you rebuild back type 2. Okay? Now let's talk about, now what is an animal let's talk about the geese and ducks. They will get up and fly all day and never stop flying. They're all type 1, endurance, dark meat muscle. Have you ever noticed the marathon is never won by somebody who look big like Manute Bolt or some offense, some linebacker or running back in the NFL? Marathon runners look like they need to eat supper, right? They look thin, right? Because they have converted their body to all type 1 fibers. And they can go run 23 miles without stopping. Is that not amazing? A lot of those people will be very thin, very small. A lot of the world-class marathon runners are from places in, like for example, Kenya and some of the African countries. And some of that has to do with, one of the studies I saw is one of the tribes in Kenya that has a tremendous number of great distance runners. American Indians made arrows and killed the buffalo and ate it. They would run the buffalo, their water buffalo, they would chase the animal they eat until it died of exhaustion. It may take 2 or 3 days of running that animal. And we think that may have helped them evolve to have a little bit more advantage at long-term running. Now, not everybody, but at least some of them do. Has anybody in here ever eaten duck or geese? Completely all dark meat, and I think quite nasty meat. I did not like it because duck is a dark meat. But I just find that fascinating. So offensive linemen are all big and showy because the whole play is 3 seconds. But you take somebody like a basketball player, they need a mixture of both, right? Because you need a little bit of endurance, but you also need that strength. So you think it's somebody like Stephen Curry, he doesn't look very athletic, in my opinion, right? But he's the greatest basketball shooter probably I've ever seen. So anyway, the Russians used to take babies and take a plug out of their arm and tell which muscle they got more of. And if you had type 1, you were what? An endurance runner. If you have type 2, then you're a weightlifter, because weightlifting is all over with in 2 seconds. So the way you build your body is based on these 2 types of fibers. Now, the 2 times I've got down to 150 pounds, I would be watching what I eat, and I could not eat the protein to get the big showy muscles. I've never had the big type 1, type 2, large fiber. That's the big showy, big muscles. But I can outwalk any of y'all to Jackson in my prime because I had great endurance. Okay, so endurance is not showy. It is just the small diameter fibers. We got some pictures of this too in just a second. Now, it's a little more complicated. We have found there are different 2 types of type 2. Okay, and then we have actually recently found one that's a combination of all of them. But look at this. Baseball player sitting in the dugout uses type 1 on his back. When the player jogs out, they're using type 2. When they hit the ball, they're using type 2X. And here is an electron microscope showing you, look, dark meat, white meat. So people who have big, showy muscles, weightlifters, have more of the big white meat muscle. Here are some characteristics of them. There's a type 1, type 2, and you can tell how they fire and what they're used for. That's a short answer question about that. I think it's pretty cool. Then now they're shifting gears, looking at motor neuron units, right? And so the more single motor neurons and all the muscles controlled by that one neuron. It's slow if it's type 1, right? And a type 2, right? It just talks about how that can vary that. Look at the numbers here. Number of fibers, muscle fibers per nerve can range anywhere from, look, the fine control might be 10 muscles per nerve to the back muscles and leg muscles, 3,000 per nerve. And eye is a low number because you got movement of those eye muscles. So don't worry about that. Muscle tone is involuntary muscle contractions. And I do have a question, some multiple choice in a minute, about the different types of movement. It's coming up. Yeah, I love these because they drive me crazy. So I put these 4, I think it's 4 of them. See if they come up. Yeah, these terms always drove me crazy. So let's go over them. Isometric contractions are muscles. The muscle length remains unchanged when you contract. Now, what would be an isometric contraction? Pushing against the wall and the wall not moving, right? The muscle length remains unchanged, but you're burning ATP because you can't overcome the external force equals the generated muscle force. I can't make that muscle, the wall move. So isometric are contractions when the muscle does not move at all or its shape does not change length. Isotonic contractions are when the muscle length changes. Now, this is the one that got me confused. Isotonic concentric is when you contract a muscle and the muscle shortens. That is the way 99% of all movements occur, right? I done told you, muscle shorten, that's isotonic concentric. Now, this one drove me crazy until the next one drove me crazy until I figured it out. What is an isotonic eccentric contraction? You have tension on the muscle, but the muscle lengthens. Now, wait, Robin, muscles never lengthen when they contract. Okay, what if 2 or 3 of y'all grab my arm and laugh and I say pull down, but I try to not prevent it? I'm trying to contract, but y'all overcome it. And so the muscle does lengthen even though I'm trying to contract. That's what an isotonic eccentric contraction is. When if I hand you 1,000 pounds and you try to hold it and you can't, and your muscles fall, they lengthen because you can't. Let's read it, and it makes a little more sense. The external force, the weight of me laying 1,000 pounds on you, is greater than that generated by the muscle. So the muscle has to has to lengthen even though it's trying to contract. Absolutely one of the dumbest terms ever, but since I had trouble with it, I got one of those 4 on the test, or 3 of isotonic concentric, isotonic eccentric, or isometric contractions. One more time. No movement, shortens. That's the way normal muscles work, and the muscle lengthens because it can't handle the pressure of the weight. Pretty crazy. Oh, here they are. So here it is, concentric. That's too heavy. Eccentric, and then I can't move it. I can't move it either way. Stand still, push it against the wall. All right. Term on the test. Let's see who's awake. DOSM, DOMS. Forever, we've been calling it muscle soreness, thought to be by accumulation of lactic acid. Current research suggests more likely due to minor structural damage, especially that caused by isotonic eccentric muscle contractions. Pain may be also due to myofibrils remodeling. So now instead of calling it a sore muscle, we have delayed onset muscle soreness, DOMS. So the most effective treatment for delayed onset muscle soreness is more exercise. So get back on that stair stepper, girls, when you're hurting, or the elliptical. Once exercise ceases, pain returns. So continuing that muscle actually stops the pain. Other treatments include massage, topical therapies, acupuncture, and some anti-inflammatories may benefit. So delayed onset muscle soreness, DOMS, is a term tomorrow. Skeletal muscle performance. Let's see if I'm about through with this thing. I'm about done here. I'm trying to knock it out here. Nothing much here. Oh yeah, look at the picture here. I think you'll like I'm gonna get the picture. This shows what weightlifting endurance exercising can do. I think there's a picture that summarizes it. Look at this. I'm gonna summarize this. coming up. Here we go. So here is Elizabeth. Here's her muscles, her leg. She decides to go to the gym and she does elliptical for 2 hours a day. And look at her now. She's not going to be real muscular. She's going to lose weight, but her muscles are going to have lots of what? Increased cellular respiration, increased mitochondria. And look at all these new blood vessels supplied to her legs and her arms. Because she's now doing elliptical an hour and a half a day. But let's say now Elizabeth decides to go lift weights. And so now she will get bigger. Look how much bigger that is. You increase the myofibrils, increase the diameter of the muscle fibers and myofibrils, and you get bigger muscles. So weightlifting makes you tear the myofibrils and you build them back bigger. Or you can do Robin. Robin sat and watched TV during the entire pandemic, COVID event, and he got atrophy and his muscles got smaller. So that picture summarized about 8 slides, right? And what happens when you endurance train, resistance train, or sit and watch TV and eat. Now, how many of y'all done the cross training? That's a big deal now, right? Where you do a little bit of both, right? You lift weights while doing endurance training, and that can lead to some very good body production of body size and stuff. Fatigue is inability to maintain that contraction, right? So fatigue is when you have a muscle fatigue. It could be deleted metabolites, could be decreased availability of oxygen, or accumulation of chemicals in the fibers such as ADP, calcium phosphates. Even environmental conditions like extreme heat and sweating can cause electrolyte imbalance or disturbance. So fatigue is inability to maintain an intensity level of an activity, for example, exercising or playing a game or sports. Here's another one. I think this could be on the test too. Seems like I put this somewhere. I just love these abbreviations. EPOC. Now, the old books use this. They call it oxygen debt. And there really is no oxygen debt in your body. Instead, this is excessive post-exercise oxygen consumption. This is when you keep breathing after you exercise. So when I've been watching TV for 5 hours, when I run to the kitchen and make a sandwich and grab some food and run back to my Barco lounger with my TV tray, I'm doing this. Okay, all that is increased rate of oxygen I need to take that energy. So it allows the body to recover from exercise-induced homeostatic imbalances. So you just bring more oxygen in to break down that energy that you may have overdone it a little bit. So you need more oxygen to break down more sugar to make more ATP. Last little section here, and I'm not going to go crazy on it, is talking about the different types of muscle contractions. Smooth muscles have those peristaltic waves, and they form sphincters. And they actually show a picture of this. Take a look. They have intermediate filaments inside them. We're going to see it here in just a second. Check it out. I'm going to get to it. And here's what they look like. So they don't have the striations, but they have protein filaments. And when they contract, look what they do. They have a protein called calmodulin. Calcium binds to it, so calcium triggers them. And look what happens. The muscle wads up like this. Come on, there we go. Relaxed. Actin and myosin grab each other, you form cross bridges, and it bubbles up and shortens. So it wads up like a piece of paper. Now check this out. This is pretty wild. Smooth muscles can contract up to 80% of their resting length. Skeletal muscles only contract 30 to 40% of their resting length. Only about 1/100th amount of ATP is required for smooth muscle to contract versus the amount of energy needed for skeletal muscle. Okay? So that kind of shows you inside. So it don't have striations, cross striate, it has cross. It doesn't have the pretty red lines, but it wads up when it contracts. Actin, myosin contracts together, and it wads up like this. And they have gap junctions, so you can get all of them to fire together. Did we lose somebody? That's usually the sound that we lost somebody. Cardiac muscles, mitochondria account for 30% of their cytoplasm, lots of energy. Intercalate discs or electrical gap junctions allow them to communicate with each other. Unlike skeletal muscle, they have pacemaker cells that autorhythmic beat on their own. So heart muscle beats on its own. We can pull it out of the body and it will keep beating. Pretty fascinating. All right, that concludes the chapter. Do we want to go Do we have time to play the video one more time? Do y'all want to do that? Let me look at the class here. Hold on, I'm trying to get out of this. Oops, I'm messing up here. All right, let me go back to our. There we go. There's my class. So do y'all want to take a minute and try to go back and look at the video? Sadie's shaking her head. She's had enough. Okay, I think I'm just gonna let y'all watch it on y'all's own. Okay, I think now if y'all go back and watch it, it'll make a lot more sense. And I hope y'all didn't mind me showing it first the other day, but I do think that was good because it made you really go look into it. I know several of y'all went and watched it last night because it is scary. Now look, guys, I told y'all the first day, there's some hard stuff to understand. And to me, one of the most difficult things in the whole book is muscle contraction and action potential. I do think, though, that energy is more scary because it involves a cuss word called chemistry. Remember how y'all all hate chemistry? Okay, so that makes the energy chapter difficult. That'll be over in digestion. All right. If we have time today, I may show it in lab. We have a little time. We might watch it in lab if you want to. And I may tell Philip. I don't know. Is Philip doing the muscle? I don't know if I told him to do the brain today. Is he doing the brain or bones today? Y'all probably doing bones.
I think he's doing bones still.
Okay, I may see if he wants to switch it. It don't matter if y'all do the quiz today, but I do think letting y'all see that brain a little bit today because the final is next Wednesday. So after today, we got one more lab, and y'all really need to look at some of those bones, right? Okay. Is everybody okay? I don't think we have time to really watch a video. I've got 9:55. So what do we call it a day? Okay. And I'm looking here, and I think I went over in the last 15 minutes. We went over 1, 2, 3, 4, 5, 6. Six of the terms. Here's another one that I don't think I went over this. So I think I blew through this somewhere. I don't remember talking about this. But how many of y'all have heard of rigor mortis? It's in the book. Rigor mortis is when the muscles contract after somebody dies. And it was a slide, I think, somewhere in the muscle chapter, and I must have flew through it. But here's what happens. About 4 hours after you die, calcium leaks out of the sarcoplasmic reticulum, and it binds to troponin, and you get a muscle contraction. So all skeletal muscle contract, okay? And then about 8 to 10 hours after that, there's not enough ATP to pump it back in, and so the muscles just decompose, and then you relax. So when they find a body in CSI, police find a body, they'll put a thermometer in it and see how long it's been dead based on the temperature and the state of rigor mortis, and they can predict very accurately how long that body's been dead. Now, I had an uncle that was a mortuary science person, and he worked in a funeral home for about 2 years, and he couldn't take it because that is negative, man. People dying and people crying, and that's a real negative job, although they make a lot of money, and we have a program in DeSoto that some of y'all may want to go into and make a lot of money at a funeral home. But he ended up selling mortuary supplies for 40 years. And he told the story of the Delta where a man died, and back in the day, they used to have a wake where you'd take Uncle Billy, put him in a casket, and set him on the coffee table in the den, and all the men would stay with Uncle Billy until they buried him the next day. And I always think this is kind of weird because once you bury somebody, you only come by every once in a while, maybe every day for a week or two, then maybe once a month, and then over time, you go by every 10 years. They were in the Delta. Uncle Billy was laying on the coffee table in his casket, open casket. And undoubtedly, they processed him very quickly, and he had not had rigor mortis yet. And he sat up at 2 a.m. He sat up in the casket, sat straight up, and wanted to grab a sandwich. Like set up. They said that people went crazy that 2 boys jumped through a window to get out of the house. And he said the preacher told him that they had a revival on Sunday. About 20 people got baptized. Everybody went forward. People got right. But it was rigor mortis, okay? It was not the awakening of the dead yet, okay? But isn't that wild? But you can see movements after death. It's called rigor mortis. All right, come. And that's in the book. It's in there. I just skipped it somewhere, and I apologize. But it's kind of fast in summer school. Any questions before we go?
I have a question about the test. Do we not have to label like the picture of the anterior, like the person standing and
I
anatomical.
said the superficial muscles. Yeah, I said there's 24 of them
Okay,
on the left.
that's what I was writing down.
Yeah, the front, what is it? I don't have the number, 9, the one we started at, just
Okay.
that. Good question, Olivia. That's the only diagram you got to label tomorrow, right? Is the superficial muscles. Front view, rear view. Hold on. I have my book. Good question. Let's don't miss that. That's 12 points. Page 292 and 293, figure 9.6 and 9.7. 9.6, 9.7. Come on, right? Remember that, right? And it's also, I believe, on the lab final that we have ready for y'all. That's the only thing we're going to do for muscles in lab. Okay, don't forget, don't walk on the first floor. They are waxing the first floor this morning. Go up the stairwell. But we will take our test down there in the morning like we normally do in those 3 rooms. All right? They promised me they'd be through this afternoon. They're probably through right now. It's drying. Okay. We have a quiz today in my lab on the sheep brain pictures, right? And I actually set up there late yesterday, late yesterday. I think I have those ready. I may grade them very easily. They didn't photocopy super great, but it is the exact pictures I told you to know. Okay? I'll see y'all at 11, and I'll stay on if anybody has a question. I'll stay on a minute. Thank y'all. Thank y'all today. Good stuff. Let me stop recording, but I'll stay on for a minute.